So now we're ending our couple of talks on transportation. And as you probably noticed by looking at our lineup of talks, uh, mathematical, statistical, and data science actually encompasses a lot of topics. And now we're shifting to something biological. And to give this talk would be Dr. Presbitero and Alva.
Okay. Good morning, everyone. So let me share my video. Good morning. So thank you so much for having me. And it's good to see familiar faces, familiar names. So yes, just as Ma'am Ray has mentioned, so we're going to jump right into another topic. So this is a topic of my PhD dissertation. So let me share my screen. So I am quite certain that most of us are very familiar with the font of my title. So anyway, enough of that. So this work was a part of a huge work dedicated towards understanding the human immunity. Most specifically, the human innate immune response. And this concept was actually born inside the metro station. So I was sitting in the metro, I was sifting through my notes of the human innate immune system. And then I noticed a very peculiar behavior of a subsystem of the human innate immune response, which I will later talk about. And this idea became simulations and simulations into articles. So my name is Alva Presbitero, and these are my co-authors. So this article was written when I was working with ITMO University in Russia, as well as University of Amsterdam. So before diving to the concept, to the world of the neutrophils, so let me first introduce you to the human immune system. So the human immune system is a complex yet delicate regulatory network of highly specialized cells, tissues, and organs that work together to defend the body against these so-called foreign invaders. And this remarkably effective structure protects us from getting sick because of various diseases. Now, the human immune system has been modeled in multiple ways. One of them was agent-based modeling, and actually this is still an active, evolving field. Second would be, of course, cellular automata. Next one is ordinary and partial differential equations. So we have also modeled the human immune system using ordinary differential equations. And for this work, we want to find out or to show if the concept of evolutionary game theory could explain a subsystem, a very important subsystem of the human innate immune response. So the human immune system has two major arms. So the first one would be innate immunity. The second is the adaptive immune response. But I will be focusing on the innate immunity. So the innate immunity is the first line of defense. So it is present in all individuals at all times. It is immediate. Therefore, it is very fast acting. Now, once your body is exposed to pathogens, your human innate immune response is the first one that would react to it. It is non-specific, therefore it could only react from the self, from the non-self, and the self. However, it does not generate lasting protective immunity. And this is the overview of the innate immune response. And for this work, I will be only focusing on this tiny subsystem, however, very important part of the human innate immune system. So let me first give you an overview of how the innate immune system works. So first, we would have the presence of inflammation triggering moieties, or what I would call ITMs. So these ITMs could be either LPS, lipopolysaccharides, ATP, ADP, and so on. So anything that would trigger the inflammation in the body. And these macrophages, these dark blue things you see right here, so they will try to phagocytose these ITMs. And in that process, they would release these so-called pro-inflammatory cytokines, right? So these fork-like structure over here. And these pro-inflammatory cytokines would open up the endothelial barrier. So the endothelial barrier separates the tissue from the bloodstream. And after this, these resting neutrophils, which are found in the bloodstream, they would go right through, they would pass right through the endothelial barrier, and they would go to the site of inflammation, where they would try to neutralize the ITMs. So if these ITMs are already neutralized, they would go into a programmed death called apoptosis. And after which, the activated macrophages would engulf these apoptotic neutrophils and the body is happy again. So the body is healthy. However, this does not happen all the time because sometimes when inflammation is too intense, too severe, or maybe inflammation repeats itself, right? The neutrophils go into another more violent death pathway, which is called necrosis. So with necrosis, the cytoplasmic content of the neutrophil spills towards the surrounding tissue, which causes tissue damage. And this actually aggravates the inflammation in the body. Now, this seemingly paradoxical phenomenon fuels the inflammatory response by triggering the recruitment of additional neutrophils into the site of inflammation. Now, what we want to do to understand in this work is to answer this question. How is this delicate balance between apoptosis and necrosis maintained? Now, this behavior is actually observed everywhere in nature, just as the case of thumping rabbits, where they thump their paws so that they could give a warning to the rest of the community that a predator is coming. However, in this way, they would actually expose themselves, right? So the rest of the community would be able to run away, but this rabbit gets left behind. So another example would be the vampire bats, as they also display reciprocal altruism, since they share their food with the other vampire bats, right? And the third example would be the social insects, such as the ants, because the workers tend to just work all their lives, and there's just a queen ant that reproduces, right? That has a responsibility of reproduction. So what is game theory? Game theory is a study of mathematical models of conflict and cooperation between players. So in our work, we define a player as a tissue centered at the neutrophil. And a player can have two strategies. It can either go into necrosis, which is a violent death pathway, which in the context of game theory is what we call cooperate. And the other strategy would be apoptosis, which in the context of game theory is called defect. Now, this is evolutionary game theory because there is an application of game theory to biological population in such a way that a player can only choose one strategy in its entire lifetime. And this is the rules of the game. So let me try to explain it to you. So this is a symmetric game in the sense that it doesn't matter whether you're playing player 1 or player 2. If player 1 goes into necrosis, again, necrosis is a violent death pathway. And in our case, this is called cooperation, as it sacrifices, right? It sacrifices for the sake of the organism. So there is a probability of Q, of the player to go into necrosis at Q. If player 1 chooses to go into necrosis and player 2 chooses to go into necrosis as well, so player 1 suffers the cost of local tissue damage. And player 2 also suffers the cost of local tissue damage because both of them are doing necrosis, or choosing necrosis. Now, if player 1 chooses apoptosis, it receives the anti-inflammatory benefit of apoptosis brought about by the production of anti-inflammatory cytokines. However, if player 2 goes into necrosis, it not only suffers the cost of local tissue damage because it's going into necrosis, it receives the benefit coming from the apoptotic entity. So it has the benefit B apoptosis over here. Now, if both players go into apoptosis, they will both receive the benefit of apoptosis. So with that, we calculated the average fitness of a player. So what we have here on the last term would be the cost of the remaining ITMs in the system. Now, the goal here is that to somehow neutralize the ITMs in the organism. So we calculate the optimal strategy by simply taking the derivative. And we come up with the optimal population, which is P is equal to Q. So this would be the population of necrosis. And these terms, so I will later explain what they are. And these should follow these constraints over here. So these are mathematical constraints. So using our very simple model, we calibrated it with the data that we found in literature by Terina et al. Over here. So we were able to show that somehow it seems that the percentage of necrotic neutrophil population follows a power law behavior. However, we cannot really say this for sure, mainly because we only have 4 data points left. So using this very simple model over here, what we want to do now is to understand what these parameters mean. Now, this is under the assumption, of course, that over time, the body, the nature has chosen these parameters so that the organism would, to maximize the survival of the organism. Now, these parameters, so N here stands for the amount of ITMs a single apoptotic neutrophil could neutralize. M is the amount of ITMs a single necrotic neutrophil could neutralize. And sub T would be the total number of neutrophils in the body, that is 10 to the 11, that is so much. Alpha is the strength of the so-called global cost of the remaining ITMs. So the question is, what does nature prefer? So we plot here the corresponding parameters. So on the left, you would see a stable percentage of necrotic and apoptotic neutrophils that correspond to alpha, which is the global cost, the cost of the remaining ITMs in the system. We have the benefit of apoptosis, the cost of necrosis, and what these combination, what this structure is telling us is that maybe nature could have made necrosis damaging on purpose for the organism. Now, on the right-hand side, we plot the combination of parameters of M, which is the resolving power of ITMs, the benefit of apoptosis, and alpha, which is the global cost of the remaining ITMs. So we see here a stronger resolving power of ITMs, or higher values of M that correspond to a narrower range and lower benefits of apoptosis and cost of necrosis in the data parameter space. So what this tries to tell us is that probably nature could have chosen to maximize the organism's fitness by limiting the number of neutrophils that go into apoptosis or necrosis. Now, in order to conform with the realistic limitation of the propagation of stimuli due to the physical constraints of biological tissue, we use cellular automata. So we had two schemes, local ITM scheme and global ITM scheme. So for the local ITM scheme, the players would only look at the local intensity of the ITM. So it would just look at the neighbors, right? Now for the global ITM scheme, it would take into consideration the overall intensity of the ITMs in the system. And what we actually saw was that the neutrophils need sufficient information. So this would be in the global ITM scheme regarding the intensity of the inflammation. And what this could probably mean is that biologically, the stimuli that originates directly or indirectly from the sources of ITMs, which could be pro-inflammatory cytokines and other substances, is required for these players to actually decide on whether they would go into necrosis or they would go into apoptosis. Now, in summary, by adopting an evolutionary perspective, we were able to identify the driving mechanism that leads to the delicate balance of apoptosis and necrosis. And using our simple model, we are able to pinpoint that actually the global cost of remaining ITMs is the driving mechanism that reproduces the percentage of necrosis and apoptosis observed in data. So more of the details of the paper can be found in the link on your screen. So thank you so much for having me. And I think the next part would be the question and answer portion.
Okay, so thank you very much, Alva.